In earlier classes, we have learned how to perform the operations of addition, subtraction, multiplication, and division on numbers. Each one of these operations was performed on a pair of numbers to get another number. Similarly, there are some operations which, when performed on two sets, give rise to another set. We will now define certain operations on sets and examine their properties. You are in Mathematics of Engineering. Moving on to the third property, which is difference of sets. The difference of the sets A and B, in this order, is a set of elements which belong to A but not to B. Symbolically, we write the equation as set A less B and read it as A minus B. Take for example two sets where set A would have the elements of the numbers 1 until 6 and set B would have 2, 4, 6, and 8. Let's check A minus B. Since both sets A and B have the elements 2, 4, and 6, we would have A minus B as 1, 3, and 5, since the elements 1, 3, and 5 belong to A but not to B. Now what happens if with the same examples we are going to work on B minus A? Again, since both sets A and B have the elements 2, 4, and 6, we would have B minus A is equal to 8, since the element 8 belongs to B and not to A. Therefore, the set B minus A is equal to 8. We note that A minus B is not equal to B minus A. Let's take another example, setting off with set V with the elements A, E, I, O, U, and set B with the letters A, I, K, and U. We are asked to find for V minus B and B minus V. Having their intersection, we have V minus B taken as the elements E and O, since the elements E and O belong to V but not to B. And for B minus V, our element would turn out as K, since the element K belongs to B but not to V. It would be worth noting that for joint sets A and B, the sets A minus B, the intersection of A and B, and B minus A are mutually disjoint sets. That is, the intersection of any of these two sets is the null set. Let U be the universal set which consists of all prime numbers, and A be the subset of U which consists of all those prime numbers that are not divisors of 42. Thus A can be said as all the values of X, where X belongs to U and X is not a divisor of 42. Checking, we see that 2 belongs to U, but it does not belong to A because 2 is divisor of 42. Similarly, 3 belongs to U, but 3 does not belong to A. And lastly, 7 belongs to U, but also it does not belong to A. Now, 2, 3, and 7 are the only elements of U which do not belong to A. The set of these three prime numbers, that is the set 2, 3, and 7, is called the complement of A with respect to U, and is denoted as A prime. So we have A prime is equal to 2, 3, and 7. Thus we see that A prime is equal to all the values of X where X belongs to U and X does not belong to A. This leads to the following definition, stating, let U be the universal set and A a subset of U. Then the complement of A is the set of all elements of U which are not the elements of A. Since A prime has been denoted as all the values of X where X belongs to U and X does not belong to A, we can say that A prime is equal to U minus A. Let's consider an example. Suppose we have set U with the elements of the numbers 1 until 10 and subset A with the elements 1, 3, 5, 7, and 9. Find A prime. We note that 2, 4, 6, 8, and 10 are the only elements of U which do not belong to A. Hence, we can say that A prime is equal to 2, 4, 6, and 8. If A is a subset of the universal set U, then its complement A prime is also a subset of U. It is clear that the definition of the complement that for any subset of the universal set U, we have the prime of A prime is equal to A. Now, we want to find the results of the prime of the union of A and B and the intersection of A prime and B prime in the following example. Let U have the elements 1, 2, 3, 4, 5, and 6. Set A would have the elements 2 and 3, and set B with 3, 4, and 5. In order for us to prove that the intersection would be similar with our union of those primes, we start off with the left side having A union B and take its prime. So, working on with our union, A union B would turn out as 2, 3, 4, and 5. Taking its complement would be using our universal set that would have 1, 2, 3, 4, 5, and 6. Placing them together, we would have the complement given this time as 1 and 6. Working on the right side of the equation, that is, the intersection of A prime and B prime. Starting off with our A prime and using the universal set with the elements 1 until 6. Placing our set A with the elements 2 and 3, we have our complement of set A as 1, 4, 5, and 6. Similarly, having our universal set and that of set B, which is 3, 4, and 5, we would have our value for complement of B, which would be 1, 2, and 6. Learning that for set A prime, the values would be 1, 4, 5, and 6, and that with set B prime, the values are 1, 2, and 6. Taking their intersection, we would find that intersection of A prime and B prime would be 1 and 6, which would have the same answers or elements taken earlier from the complement of the union of A and B. There are some properties of complement sets. First are the complement laws. The first complement law states that the union of set A with its prime would still be equal to the universal set U. The second complement law states that the intersection of A with its prime or complement is still equal to null. The second property is what we call De Morgan's law. It states that the complement of the union of two sets is the intersection of their complements, and the complement of the intersection of two sets is the union of their complements. These are called De Morgan's law. These are named after the mathematician De Morgan. The third property is what we call law of double complementation, which states that the complement of A prime is just equal to set A. The law of empty sets states that the complement of a null set is the universal set. The last property is what we call law of universal set. It states that the complement of a universal set is null.